Hey there, thanks for joining in. For the next few minutes, I'd like to talk now about whether two events are independent of each other. This is going to be important to know because we might want to know the likelihood of two events happening at the same time, or we might want to know the probability of an event happening given that we know something else. So this is one of those fundamental concepts in statistics that's going to keep coming up over and over again. It's a good idea to practice it. So let's dive right in. What do we mean if two events are independent? Simply, two events, A and B, they're going to be independent of each other if the fact that A occurs doesn't affect the probability of B occurring. Right. So let's say you've got two events. Event A is that you're tossing a coin, and event B is that you're rolling a dice. Now the probability that the coin comes up heads is completely independent of what you roll on the dice, right? You could roll a 1 on the dice. Probability of that coin is still going to be whatever it is, 50-50, let's say. And if I tell you that, oh no, I rolled a 6 this time, that shouldn't really change your idea of what the probability of flipping a heads is going to be. These are two separable, independent events, right? One doesn't affect the other at all. So what about dependent events? Two events are dependent if the outcome of one affects the probability of the other. So, for example, let's say that event A is that it rains today. Well, I don't know whether it's going to rain today. Let's say it's a 50-50 chance. But what if I told you, and you didn't know this before, that there was a hurricane yesterday? Well, just knowing that, doesn't that affect the likelihood of rain today? If there was a hurricane yesterday, the likelihood of rain today is probably closer to 100%. Right? So the mere fact that there was rain yesterday does affect the likelihood of event A, of rain today. Or one last example for dependent events. What's the probability that you're going to become president? Let's say it's 1 in a million. Okay. Now, what's the probability that you become president given that you're dead? Well, if you're dead, you can't become president. Very sorry. So the outcome of you being dead has now changed the probabilities of rain today, of becoming president. So here we see that outcome B did affect a different probability of outcome A, namely becoming president. So that's kind of our intuitive understanding of what it means for two events to be dependent. Let's look at something a little bit more quantitative, more numerical, and let's work out that example. Of card counting examples, so let's do one of those too. Let's say that you're pulling two cards from a standard poker deck, a deck of 52 cards. And you want to know what the probability of drawing an ace on that second draw. Does that probability depend on what happened on the first draw? Let's have a look. Let's say that you drew a king on the first draw. All right, so on the second draw, there's not 52 cards left anymore. There's only 51. But since you drew a king, then there's still 4 aces in the deck. So the chances are that you've got 4 out of those 51. So the probability is 4 out of 51, which is about 7.8%. But what if you did draw an ace on that first draw? Well, on the second draw, there's going to be only 3 aces left out of the 51 cards. So that probability is going to be 5.9%. So you can see that the probability of an ace on the second draw depends on the outcome of a different random event, namely whether you drew an ace on that first draw. So here we've got this, this more complete example. We have a table that describes a bunch of different scenarios. First we have two variables, A and B. A can take on one of two different values. So A can be a 1 or A can be a 2. Right? So A is the random variable and it can either take on this value or that value. Likewise, B can take on one of two values, B1 or B2. Maybe these are like two different coin flips or something like that. These are not necessarily fair coins, but we've got two events, each of which can take on two distinct values. And we want to know whether A is independent of B. So let's remind ourselves what the definition of this is. What does it mean for A to be independent of B? It means that the probability that A takes on a particular value is the same even if we're told the outcome of that other thing. Right? So the probability of a heads is the same even if I told you the outcome of a roll of a dice or something like that. So let's prove whether these two events, A and B, are independent of each other. Okay, so I need to calculate the probability of A. Now A takes on one of two distinct values, so I'm going to need to know the probability that A is A1, and I need to know the probability that A is A2. So how do we do that? Well, imagine that you ran this whole experiment of flipping A's and B's 100 times. Then you would expect 30 of those outcomes to be A1, B1, because the probability here is 30% of that happening. Probability of A2, B1 is 20%, so you would expect 20 out of those 100s to be A2, B1. Likewise, you would expect 30 and 20. So back to our question, what's the probability that A comes up A1? Well, we had here 100 total recurrences of this experiment, and let's see, 30 came up A1, B1, 30 came up A1, B2, so that's 60 for A1 out of the 100. So that's 60%. What about occurrences of A2? Well, we had 20 and 20, that's 40. Out of 100, that's 40%. And we want to know whether the probability of A being A1 depends on what happens with B, and likewise for A2, if that depends on what happens to B. So let's keep working. What is the probability that A is A1, given that we know what happened with B? Let's say it came up B1. If it came up B1, we're in this row right here, right? Which means there were 50 occurrences that we need to deal with. Now, out of those 50, how many were A1s? 30. So 30 out of 50 is our 60%. Hey, that looks familiar. Yeah, all right. Now, does this probability change if B had been something else? What if B had come up B2? So now let's look at this row. All right, well, the probability of A1, so now B2 happens, so it's one of these 250 occurrences. What's the probability of A? It's now 30 out of 50. A different 50, but it comes up 60% too. So, well, this is cool now. No matter whether we know what happened to B, whether it was B1 or B2, or we don't know what happened with B, the probability of an A1 happening is always 60%. So this is looking good for independence. Now, what about the probability of A becoming A2? How does that change if we know that B1 happened? Now we can use the rule of complements to do this very quickly, and it'll be 1 minus this probability. Right? So it'll be 40%, 40%, which will be our 40%. But rather than resorting to a different statistical rule, let's just go through the same exercise again. Okay, so we're told that B1 happened in this scenario. So we're back up to our first row. What's the probability that A2 would happen? Well, 20 occurrences happened out of 50. Which is 40%. And then what about the probability of A2 given that B came up B2? Well, if B came up B2, then we're here looking at these 50. Right, probability of A2, that was 20 out of the 50. And that's also 40. So 40, 40, 40. Probability of A2 is 40%, even if we know what happened to B. So yeah, we can say A is independent of B. Is B independent of A? Let's work through the math behind this. What do we mean by B being independent of A? It means that the probability that B comes up something, whatever, is the same even if I tell you what happened to A. So what would be the probability that B comes up B1? Okay, so let's go through this whole exercise again. These are our joint probabilities. So the probability is 30% that it would come up A1, B1. So if we did this thing 100 times, we would expect 30 occurrences to happen there. The probability of A2, B2 is 20%. So if we did this experiment 100 times, we would expect around 20 occurrences and so forth. So let's fill these values in. This is the same table as from a slide ago. I just cleaned up the table. So what's the probability that it comes up B1? Well, we've got 50 occurrences out of, well, 30 plus 20 plus 30 plus 20 is 100 total. So we've got 50 out of 100, which is 50%. What's the probability that B comes up B2? Well, B can only be either B1 or B2. So if 1 is 50%, then by the rule of complements, this one should also be 50%. And we'd like to see whether these two probabilities up here, these guys, change if I tell you what happened with A. Let's give it a look. What's the probability of B1 given that A is A1? All right, so if A1 happened, then we're in this column. This is one of, so there's 60 occurrences where A1 happened. 30 of them, B1 also happened. So it's 30 out of 60, which is 50%. What's the probability of B1 given that A came up A2? Right, so now we're here. A2 happened. So we're looking at these 40 occurrences. B1 happened in 20 of them. Lo and behold, that's also 50%. In fact, we're going to get nothing but 50% on this slide. So the probability of B1 is 50%, whether we don't know what happened with A1 or that we do know what happened, with A, that all these are all 50%. What about for B2? I think you get the idea. But let's work it out. You can always fast forward. Given, and I'm just going to be quick with my notation, given A1. So given that this thing happened, we're looking at one of these 60 occurrences. How many of them were B2s? 30. That looks like 50% to me. And what is the probability of B2 given that A2 happened? Now we're here. It's one of these 40 occurrences. We're in this column. B2 given A2, that's 20 out of the 40. Which also looks like 50%. So these guys and these guys also all came up 50%. So our probability of B2 is 50%. Doesn't matter what happened with A1 or A2. It's 50%. So yes, B is independent of A. Independent of A. Okay, so A was independent of B, and now we prove that B is independent of A. I have another video that shows whether it's always the case that independence of A from B implies the independence of B from A. You should check out that video. Now, let's do a slightly different example. The same math, but with different probabilities associated. Are these two variables, A and B, are they independent of each other? Right? So A can still take on two different values, A1 and A2. B can still take on two values, B1 or B2. But there was a nice little symmetry to our variables here that seems to be missing here. Does that imply something about independence? Yeah. But let's give it a look. All right. So is A independent of B? That means it's probability of A given B. Is that the same thing as just the probability of A? And what's the probability of A? It can be a probability of A1, probability of A2. So we need to be more specific. The probability that A comes up A1, yeah, what is that? Oops. Well, if we ran this experiment 100 times, we'd have 20 occurrences of A1, B1, 40 occurrences of A1, B2, and so forth. So what's the probability that we come up A1? Well, we'd have 60 A1s out of 20, 30, 60, 100 total. So what's the probability of A1? It's 60 out of the 100. What's the probability of A2? Well, by the rule of complements, we knew that's got to be 40%. 1 minus the 60%. It's 10 plus 30 is the 40 out of 100. So what's the probability now given that B happened? Let's see, what's the probability of A1 given that we know what happened to B? And let's say that it was B1. So let's say it's one of these 30 things that happened. 20 plus 10 is 30. So, so 20 of those 30s were A1. So that's a 2/3 chance, which is 66%. Well, hey, hang on. We can stop right here. The probability of A changed once I told you what happened with B. Let's see, what's the probability of A1 given that B2 happened? All right, so if B2 happened, then we're at this row, we would have 40 A1s out of how many? Well, we know that, there we go. So, so 40 divided by what? We know that, that B2 happened. So it's one of these 70 things. So it's one of these 70 things that happened. 40 out of those 70 are going to be A1s. What's the probability? What's 40 divided by 70? I don't know. 57%. And so notice the unconditional probability of A1 happening is 60%. If I tell you that it came up B1, then it changes. If B2 happened, then that changes. A is dependent on B. And we can actually stop right here because we've proven our point. Is B dependent on A? Let's work it out. So we need to know the probability of B and then compare that to the probability of B given that we know what happened for variable A. What's the probability of B happening? So it's going to be 30% or 70%. All right, so B could take on one of two values with probabilities 30 and 70. What's the probability now, given that we know what happened to A? So if we know what happened to A, let's say A happened and it came up A1. Well, how many of these were B1s? 20 out of the total 60. Which is not 30%. So 2/6. What's 2/6? 2/6 is 1/3. I shouldn't have had to look that up. I'm embarrassed. So we get a different probability. So we can stop here as well. B is dependent on A, just like A was dependent on B in this example. So we just saw that A was dependent on B. What can we say about the other direction? Is B independent of A or is B dependent on A? Does B depend on A? Well, let's find out. We'll be a little quicker with our math. When we're asked, is B independent of A, we want to know whether the probability of B is the same once we know what happened to A. So what is the probability that B comes up B1? All right, so what is this probability? Right. Well, if we ran this thing 100 times, 20 would come up this way, 10 would come up that way, 40, and 30. So we would expect 30 occurrences to come up B1 out of the total 100 for 30%. Does this probability change once I tell you what happens with A? Like, let's say I told you A happened and it came up A1. Okay, so now there are 60 occurrences that we need to care about. How many of those had B1 happen? 20. All right, so the probability of B being B1, given that I know now that A1 happened, was 20 out of 60, which is 2/6, which is 1/3, which is 33%. And these two probabilities are different, 30%, 33%. So no, B is not equal to B given A. B is dependent on A, just like A was dependent on B. All right, so there you go. Thanks for watching.